Okay, so what we're going to take a look at in this video is a couple of things that have started cropping up with graphs that we need to cut out straight away. So I'm going to start off by looking at what is wrong with this graph. So this comes from an experiment where we're investigating the current potential difference characteristic for a filament bulb. So there are two main problems with this graph. The first one is illustrated by this movie poster over on the right hand side. This is the movie poster for the film The Blob, as you may guess from the name on the poster. And that's owing to these things that I'm seeing on a graph, which I'm not expecting to see on a graph. I'm seeing blobs. I'm like, we've been plotting graphs for a few years now. We've never plotted giant blobs on our graphs before. Suddenly I ask people to use Excel, suddenly we're getting large blobs. What's going on here? So the point I'm trying to make is when we do graphs, we should be plotting our points with an X, not with a giant blob. Reason being, an X allows us to mark a precise point. A blob covers a wide area, and we want precision in our graphs. So that's the first issue with this graph. The second issue, which is the main feature of this video, is we've not got a line of best fit. We've got loads of lines joining the dots. Again, something that's never been okay in physics, and yet it keeps cropping up. And that's the main content of this video. I'm going to look at when this is appropriate to do, because there are times when it is appropriate to join the dots. None of those occur in physics, I would point out, but there are sometimes it's a valid thing to do. And there's a lot of situations where it's not valid to do, and those are the things that come up in physics. So let's talk about that in a bit more detail, rather than just having those general rules. So there is a time where joining the dots is correct, but we will never come across that when we're doing physics. Okay, so that's our first big picture thing. So it's acceptable in scenarios where there isn't a causal link between the quantities on the axes, and which means we're not trying to find an equation that links them. So let's have a look at a specific example of that in action. So let's say we're monitoring someone's heart rate over a period of time. Okay, so that would be a classic example of a non-causal link. So somebody's heart beating doesn't cause time to pass. So there's no causal relationship there. Time passing, again, doesn't cause someone's heart to beat or beat differently. There's no causal relationship in there. Someone's heart rate will change because they start exercising, because they've been scared, because they're meditating. All of these, those are your causes, but there's no causal relationship between heart rate and time. So because of that, we would never be trying to come up with an equation linking heart rate and time. Okay? Because there's no causal relationship. Equations are for causal relationships. So that's why it's okay to join the dots up here. Because the reason you would do that is to estimate the heart rate at a time we haven't measured. So let's say we want to know what the heart rate is or at 24 seconds. So we go, okay, here's 24 seconds. We go, I got really wonky there at the end. Let's do this properly. There you go, okay. Let's start across. Okay, so we've got a rough idea that at 24 seconds, looks like their heart rate was about, 126 beats per minute. So joining the dots in this instance allows us to get an estimate of the heart rate between 2 points. Okay, so that it can be useful. So maybe in a biology lesson where you learned about heart rate and did some data collection for that, you would definitely have joined the dots in here. It would have been a really useful thing to do to make this estimate. So that's absolutely fine. Let's look at when it's not fine. So physics is the subject of causality. We want to know which things cause other things to change. That's what we're interested in physics. And better than that, we don't just want to know which thing affects the other thing, we want to know how it affects the other thing. So we want to find a relationship between them that we can express using an equation. So we might do an experiment where we change one thing. So here, maybe we changed the potential difference and we investigated its effect on current, and we kept everything else the same so we could be sure it's the potential difference causing the current to change. Okay, so that's why control variables are so important, so we can establish causality. So if we draw one line of best fit that goes really close to all our data points, that can be described using one equation. So what we've now got is an equation that will allow us to predict current at any potential difference that we might think of. So that's why that's so useful. So if you think about the equations that you've come across in physics, so we've met V equals IR, we might have met F equals MA already, we might have met moment is force times distance, work done is force times distance. All of these equations come from doing experiments where you've changed one thing and measured the other. And from that, we've done a line of best fit and found out what the equation is. So these equations aren't something that actually exists in nature. This is an equation that's come from doing experiments and drawing a line of best fit. Okay? So that is the good section, if you like. On this right-hand side, we've got a graph where we've joined up the points. Now, if we're trying to find equations, that means on this graph, we're going to have to find 9 equations because we've got lines which all have different slopes. They all go through different points. So essentially what we're going to have to do is find out the equation for 9 lines. And then if I said, okay, so what would the current be if the potential difference was 2? We wouldn't know because that's beyond our set of data. Whereas on the left-hand side, if we've come up with an equation, if I told you potential difference is 2, you'd be able to predict what the current is. So that's actually the equation and the line of best fit are really useful. Whereas joining the dots like this just makes it horrific. And the more data you have, the more equations you'll have to model what's going on in this situation. So this is why we absolutely do not do this in physics. We want one equation, one relationship. We don't want hundreds of equations and hundreds of relationships between our variables. So let's have a look at how we find the equation if we have our line of best fit. And Excel has a tool to do this. So if you right click on your line of best fit, go to Format Trend Line, go to Display Equation on your chart. So you'll see that the equation for a filament bulb is horrific. So you can see the best fit that I found had an order of magnitude 6 in it, which means there's a potential difference to the power of 6 term, a potential difference to the power of 5 term, of 4. So it's a horrendous equation. So this is why in GCSE Physics, for example, we never look at the equation that models a filament bulb because it's horrible and it would scare a lot of people. Whereas we do look at the equation for a fixed resistor because it's nice. It's V equals IR. That's 3 terms and easy to move around and manipulate. But this is how we can find out the equation from a set of data and a line of best fit. And this equation would allow us to predict a current with any different potential difference. So we just substitute our value for potential difference that we're interested in for x in this equation, and out would pop out the value of current. That's why lines of best fit and equations are so powerful, and that's why we don't join the points in physics. So big takeaway message, never, ever, ever, ever join the points in a physics lesson. And don't plot blobs.